What I want to start with are these 4 plots right here, and just talk about how you would take a tissue sample. Anybody here have experience taking tissue samples in wheat at this growth stage? Once the head starts to crack through the boot, the most appropriate plant part to take is the flag leaf. Any ideas about how many you want to take?
More the better?
Up to a point. It gets pretty tedious. The lab, in order to have enough tissue sample, is going to need somewhere between 30 and 50 leaves, depending on the size. These are pretty good sized, so you could probably get away with 30 to 40 leaves like this, okay? Now the way you take these samples at this growth stage is, this is not a good sample, okay? It's not the whole flag leaf. Everybody see this? This is a good sample, right down to the ligule, okay? So when you're pulling them, you really want to pinch down towards the stem and then snap it, and then you're more likely to get the whole flag leaf and not tear off and get something that's not perfectly appropriate. So you're going to need 30 to 40 at this stage. Now let's say you wanted to understand something earlier. Let's say the crop's like that November wheat planted over there, it's kind of vegetative, but it's not small, so it's about 12 to 18 inches tall. Then how much and what plant parts are you going to take?
Whole thing?
Typically not the whole thing. That's for the smallest stages, like when you're at, say, somewhere between Feeks 5 and Feeks 7. Take the whole, cut off the plant about 1 inch above the surface, take the whole thing. But when you're at that taller stages, say 8 and 9, you want to take the upper 4 to 5 leaves off of the, just randomly off these plants. And again, you're going to need a lot of them because they're not real big leaves. You're going to need a lot of them. You're going to need probably upwards of 50 in order to get a good sample for the lab. So there's a different way to sample depending on the growth stage of the crop. Now, if I'm making an interpretation at this stage, what's the value of knowing my plant nutrition status from plant analysis at this growth stage?
Next year.
Sorry?
Next year.
A lot of it's going to be, kind of post-mortem. There's a few, very few things you can do here. We're going to do a couple of those. But in reality, this is your way of checking up on your plant nutrition program for the crop this year. This is about the last good stage to sample. It does, few growers use this because they get bogged down with other activities, but a lot of consultants do use a technique at this time. Another thing though, when the plants are smaller, you can do certain things. For example, which one of these are you more likely to deal with earlier plant growth? Nitrogen, sulfur, or zinc? Early plant growth, say about, but after the first joint, say around Feeks 7. Nitrogen, sulfur, or zinc? Primary macronutrient, secondary macronutrient, micronutrient. The easiest one to deal with is going to be a micronutrient. They can be applied foliarly, and they're still reasonably effective as long as the growing point isn't pretty well developed. Nitrogen, a big shot of your nitrogen should already be taken care of by Feeks 6 or Feeks 7. You should be doing that at Feeks 2, 3, 4, and 5. Now, we'll talk a little bit about this late nitrogen story, but the bottom line is that sulfur is kind of intermediate. You might do something with sulfur, but again, your chances of an economic response are somewhat less than they are with a micronutrient. And also, sulfur is a little harder to get on what you need foliarly, so you're looking at a ground application with something at a fairly reasonable rate of product. Okay, but micronutrients you could put on a couple pounds chelated foliar and you'll probably get most of your bang for your buck. So kind of remember, when you're trying to correct a crop, it's pretty much too late here except for what we're going to call, say, a late protein charge. But the younger the crop, the more of the nutrient suite you can change in this crop for an economic bang for the buck. Now, in your packet, as a guide, there's this in your handout that's talking about taking sample for nutrient analysis. There, on the second page is the section on wheat, and it shows these various types of sample you take for the different stages in the wheat life cycle, okay? By the way, there is a final sample that is taken. It's usually not done by plant growers, it's done by mills. The grain is often very well analyzed, protein content and other things depending on where it's going, feed industry, milling industry, so that grain will get analyzed. Many times the producer will not get those results back. The other thing I wanted to point out is that how you deal with these samples once you take them is very important. You never take green material like this and put it in a plastic bag, Ziploc or otherwise. Many times by the time it gets to the lab, it'll be mush. If you chill it, you have a better chance, but it's often better just to put it into a brown paper bag. This is a fancier one from Waters, but a brown craft paper bag or a white craft paper bag with a proper label at the top is very important, okay? Because it allows the plant to breathe. It allows that tissue to breathe so it won't become soggy and pulled apart by saprophytes. The other thing that's important with a lab-based sample is there's what they call a submission form, which I think there's one that's part of your packet. I may have misplaced mine here. Here it is. Again, this is the one used by Waters. It's real important that you properly identify this. It's real important that you tell them exactly what you want. Honestly, if I were you, I'd leave out the yield number. You're just inviting a lab to do something foolish. You really want to know what the status of the crop is, and you're not going to be able to predict yield off of this. There are too many other ways in which yield is going to be determined before the end of the season, particularly in wheat, how hot it gets, so how much grain filling you have and all that. But you do want to properly identify it, tell them what crop it is, tell them what your basic test you want. In a legal case, this is chain of custody information. So for those of you in industry or consultants, this is part of the legal documentation that can go with a sample in case you, your boss, your client end up in a court of law. This is chain of custody information. You should probably sign these things with a date and a time when you hand them over to a lab or put them in. Some of these will go in the mail by, say, UPS or something like that. So I strongly urge people to sign and document. You can also even indicate over here on your remarks when the sample was taken in the field and a location. Some people put GPS location information on these samples, again, as part of a chain of custody protocol. All right? Any questions on that? Now, another thing that you can do is you could be thinking about some of these other tools. But the best tool in your repertoire is your eyeballs. Now, assuming that you don't let your pink shade eyeglasses influence you, what you have here are 4 rates of nitrogen applied in the spring in 45-pound increments, starting with 0 there, 45, 90, and 135. So what I'd like you to do is take 3 or 4 minutes, start at that end, and then meet me back at the table and we'll talk about what you see. Just what do you see as differences in the status of this crop due to those 4 different nitrogen rates? Who wants to go first? What's the first thing you see?
Thicker the stand as you go down.
It tends to be thicker. The nitrogen was applied in 2 applications. One's fairly early, so it caused some additional stooling and some additional tiller survival. So what you see is thickening. Partly is some greater leaf vegetative mass, but it's also partly just more tillers per unit area, more heads per unit area as we move in this direction. What's another thing you see?
But John, is that what we found this morning when we counted heads?
I have no idea because I wasn't paying attention to what you found this morning.
It seems like the way I remember, every plot had 60.
Over there they may have, because they were applying a more uniform rate of nitrogen, except in a few places they had 0 right timings. But here, I've done some preliminary counts. There's about, between that end and about that end, there's about a third less down there. Now, by the time you reach this, there's actually a pretty similar amount of heads here, okay? But there, that's pretty pitiful.
On 0.
Yeah, on 0, okay? Now, on the other hand, if you look at this and you say, well, it has about as many heads as this, but it doesn't look as thick. So what's that all about?
I know this seemed like as you went that way, it's more uniform head size.
That's a factor. There's probably a little better uniformity, because what you have in a nitrogen-limited environment, you have certain heads. The main tiller in particular is going to scarf more and it's going to develop better and have more spikelets per head. You're also going to have, we have observed a little greater variability among plants. Some plants get a little bit ahead of the other and they scarf nitrogen that the other ones can't get. It's kind of something like you see in corn when you've got smaller plants that get started a little later. They become more like a weed and less like a viable corn plant. Wheat does a little bit of that. But another thing you'll see in here, if you were to measure it, you would see smaller leaves. These leaves have adapted to less nitrogen. They're not as big. In order to have the same amount of chlorophyll per unit area and not enough nitrogen to make chlorophyll, these leaves are actually somewhat smaller. So those leaves are bigger, and that's what makes it, gives it that filled in look. Okay? So that's one of the differences once we get past the head numbers. That's what makes those two plots. Now, do you see much difference between 90 and 135? You don't see much difference, and you won't know until the combine runs through it whether you really have a yield difference there or not. There are many situations where a crop looks better, but it doesn't yield a lick more, except it cost you, 40 cents a unit of N for 45 more units, or about 18 bucks an acre more than what this other one cost. But you have to wait. All right, so now let's take a look at technology. These are chlorophyll meters. Okay, they clamp onto the leaves. We're going to do some flag leaf here. And this is a green seeker, which is a proximal canopy sensor. Anybody remember the difference in what this is going to tell you versus what this is going to tell you about the crop? Which one is most closely related to the nitrogen nutritional status of the crop? This one or this one?
Number 1.
By number 1, you mean the first one I mentioned. Okay, that's correct. The fact that chlorophyll is pretty much directly proportional to the amount of nitrogen, not in all cases, but pretty much, this is going to give you more data that's related to percent N in the leaf. This one is going to be partly responsive to that. What's the other factor that these canopy sensors respond to? Density, biomass, okay? So you can get a number on this one that's probably going to be closer to that one with this instrument, whereas with this instrument, this is going to come in kind of puny on chlorophyll because it's kind of turning yellow, and that one's going to come in higher. So the first thing you want to do, you can tear it off, you don't have to, I typically don't. You just clamp this on the center of the leaf, about the center, you're going to get a reading. Right now it's 36. Okay? You do this about 10 times. 36. 43. Now, I recommend take your readings towards the center. In a field environment, of course, you're going to take your samples in the field anyway, but in plots, you have to observe the same rule. Don't take a sample or a measurement close to the edge. Kind of move into the center. It'll be fine. So I'm going to spread these out. Let me clear that out for you.
That was about average.
Yeah, and there's an average button. Once you get your 10 numbers, you just hit average, and it'll give it to you, okay? The way these things work, these are called active canopy sensors. They actually, when you squeeze the trigger, they emit light. Nothing really dangerous about it. Then there's a detector. The emitter is here and here, and it pulses so many times per second, quite a few actually. Then the detector is here. So you generally want to hold this at about a set different distance above the canopy. You don't want to go too much up and down because that can sometimes influence your results, although in this case I'd have to get it really high before the field of view would start spreading outside the plot. So as long as you're about shoulder length and you stay consistent, you'll be all right. Because these borders have got a little bushier, you do want to hold it over the center to get a true reflection of what the nitrogen rate did to overall plant growth, because when it hits this bushy edge, it sees more biomass, and it's going to give it a little bit of an artificially high number. But what happens is it sends a light beam down and it sends a light beam back, and it measures near infrared and the visible spectrum and does a ratio between those to create something called the NDVI, the Naturalized Vegetative Differential Index. So the bottom line is, the higher the numbers, by the way, because it's a fraction, the numbers range between a low value, like on the ground right now, it's 0.16. Over the canopy, it gets higher, 0.62. It can go up to about 0.8, 0.9. I've never seen the value even get close to 1, okay? But it's a ratio. So what you're going to do is, I want you, again, I've got 2 units, so put yourselves in teams, and you can, because this works fairly quickly, this, when you scan, you just walk over it, and it already averages 0.68. So it's already going to give you that one number average. And then your partner can record for you and all that, okay? Record your number. And then we'll look at these numbers because you're going to see some differences in the way the 2 different sensors respond to those nitrogen rates. And then in your packet, I actually have, Edwin and I went through and took samples on these, and we actually sent them off to Waters, and they were done within the past week. So they're not exactly yesterday, but they're pretty close. And then their last one was 44.4, yours is 45.7. So another 2 to 3 increments. So the biggest increment was going from the 0 to the 45, and then it got kind of leveled out at a couple of increments in chlorophyll meter readings as we went to the last 2. All right? All right. One of the things that one of my PhD did was look at the differences between individual green seeker units. It turns out that despite improvements in manufacturing, there is a challenge with certain green seeker units. They don't exactly match up real well. So you're going to see some differences here, at least at the low end. This one here was 0.49, and the other one was 0.57. The next one was 0.69, and the other was 0.64. Now that's a much bigger increase. That's approaching 13–14%. So what it's saying is, relative to the chlorophyll meter, the limitation here is as much biomass as it is nitrogen, because there's a bigger change here where the chlorophyll meter says there's a change, but it's not so great, okay? So which one do you think is going to be, at this point, we know it's nitrogen stress, but which one's going to be a bigger driver to the yield loss over there? The fact that it has less chlorophyll, or the fact that it has less biomass? Biomass. It's less biomass. It has less heads per square feet. That's showing up in the green seeker reading, and it has less leaf area. It's by far the least. These have intermediate, and that has even more leaf area. Now, as we move up, the next plot, this was about between 0.69 and 0.64. The next one is 0.72 to 0.75, so it goes up again, but not hugely, okay? And the last one was even less. It went to 0.77 and 0.74, which is literally 0.02 NDVI units. It's very little. The fact that it did go up, what do you think that's due to? Biomass between 90 and 135, or is that additional greenness from the greater nitrogen?
Greenness. A little both.
Who knows? That was my trick question. I have no idea. I doubt there'll be a yield increase, but I can tell you that it's clear the green seeker sees it. It could be a little of both, but the bottom line is you aren't quite sure without getting in there and taking a grad student's life in your hands and having them cut, measure, okay? All right. Let's see, I got to give these back. One goes this way, one goes that way. Okay? Now, you do have in your handout a reference on the chlorophyll meter. Some of you picked that up, I think, the last time. Now, returning to the chlorophyll meter is not a bad tool to understand your potential for raising protein with a late nitrogen application. We don't know a lot about this. I had one PhD years ago who looked at this question, but we got some erratic results because in many ways we didn't know what we were doing. We know that we can raise the protein of the grain with a late nitrogen application, but there are certain things that are difficult. One is timing. Should I apply it earlier than heading, say maybe early boot? Should I wait until flowers? That's something we don't know. Another problem we have is rate. We do know we're not using a liquid at this point, unless you want to burn the crop like fire. Okay? We're not going to use a liquid. So typically you're going to use a dry material, typically urea, because if you put a product like ammonium nitrate on, you're going to have a problem with the fines in it are going to be like salt and they're going to burn it really bad. Urea granules, prills, particularly good quality prills, will drift down to the ground. You still need moisture though to activate that. Okay, let's remember that. You also need a contract. Remember, what we grow in this part of the world is soft red winter wheat. Soft wheats are in fact supposed to be somewhat lower in protein because of the uses made of that flour. But if you do have a contract, you may want to raise it. But again, the way the chlorophyll meter can help you is, if you get in there and you discover I'd still recommend what we call a well-fertilized strip, like something like that 135, you put at the edge of the field for your contract field. And what you want to know is, how far below that am I? If you're a fair ways below that in the rest of the field, then there is the possibility that a late nitrogen dose will raise your protein level if that's what your contract calls for.
Well, why would anybody want high protein soft red?
You'd have to talk to a miller who knows more than I, but I've been hearing that that's a possibility for certain kinds of crackers, certain kinds of uses of the flour. But I admit, I'm not an expert on that. I don't know. I just know that it's out there and the question has come up. In fact, the question came up in the RFP from the small grain growers, as I recall. So,
I don't know why we did that.
well, I don't know why you did it either, but it was there. And by the way, it's not the first time that's come up. But we don't have good guidelines. But I can tell you that the chlorophyll meter is kind of handy. If you've got a value for the chlorophyll meter that's already at 50, and the bulk of your field is at 48, you don't have much potential to raise it. But if the well-fertilized area is 50 and the other part of the field is around 45, 44, you've got some potential to raise it. Could I tell you the rate? No. I don't know whether it would take 20 pounds of N or 40 pounds of N. That's something we don't know. But you do have some potential. If your nitrogen status at this stage is lower, you have some potential to raise protein if you need it for a contract. Okay? Let's not have too much of this, by the way, because the quickest way to get soft red winter wheat docked for excess protein is for everybody to pile on nitrogen in heading time. So remember, the bulk of your market is for soft red winter wheat at moderate to lowish protein. That's the bulk of your market. All right. In your packet, moving to the first of these pages, you will pull it out. The first one is 4-1, which is the 0. Then it's 4-2, 4-3, 4-4. Take a quick look at what you see there. You need a packet? I tell you, man. I'll be coming back to you for that once in a while. All right? So look at 4-1, 4-2, 4-3, 4-4. That's these 4 plots right here. Take a minute to look over that and then tell me what you see. What catches your eye?
Phosphorus.
Why? What about phosphorus?
It goes from low to high whenever you, for the first one, it's high and then it drops down.
Right. Why do you think that is? Why did phosphorus, when phosphorus is high in the plant here, but then it starts getting lower and lower, or at least it drops into the not as good stage as we go through?
More biomass here?
More biomass stretching out the phosphorus supply from the soil. These do have a decent phosphorus soil test, about 90 throughout. About 90. Okay? You do notice nitrogen increases. 336, 354, 384, and 429. It actually increases less going from here to here than it does for every other increment. Because the plant analysis doesn't measure just chlorophyll, it measures all other forms of nitrogen in that leaf, every other amino acid, everything else. So it says there's other forms of nitrogen in here that the chlorophyll meter is not detecting because it started to level out, but that's not what was happening with the plant analysis. So you did see phosphorus. Anything else anybody noticed about the data from these first four?
Potash is low.
Potash looks low by this. However, the well-informed person also has potash data. Soil test potash. 535, 609, 512, and 549 pounds per acre.
Bad spreading.
Course taken right in the plot. So there are certain things you have to be careful about interpreting plant analysis data. Sometimes you can overanalyze yourself, okay? You might think potassium is deficient, and maybe because of the rapid growth, when we were taking these samples, these plants were growing rapidly. Maybe these plants were kind of stretched out against the potassium supply, but the bottom line is this soil doesn't need potassium.
No.
By the way, anybody read the recommendation just below the last table on this? What's it say?
Nitrogen, potassium, magnesium.
Yeah, but how much does it recommend?
Oh no, I didn't look down.
How much does it recommend?
A half pound of nitrogen.
How much potassium?
Half to 1 pound per acre.
How much magnesium?
A half pound of magnesium.
Okay.
Foliar spray.
Anybody have any idea how much nitrogen is in this standing biomass? Probably about 180 pounds per acre. So what's a half pound going to do in that environment? Not anything.
Seemed like much.
It's called temporary greening. It makes your CPS salesman feels good. Maybe you feel good for a day or two, and then it goes right back to being yellow again. So with the macronutrients, it's very difficult to do anything meaningful at these low rate of foliar applications. You can't put on all that much high anyway. Now, here's an interesting thing. This plot is labeled as deficient in nitrogen. This plot is barely in the sufficient range. So they recommended a half pound of N over here, and they didn't recommend any nitrogen here. But yet, how much nitrogen was at least applied here relative to here? 45. So you really think a half pound of nitrogen on this is going to do very much? When it took 45 just to get it barely sufficient? Okay, let's go up. We're going to go up to 3.7 and 4.7. On your charts, it'll be 3.7 and 4.7. The only difference here, this one had, excuse me, fall nitrogen, and this one had no fall nitrogen. 3.7, 4.19%. 4.7, 4.05%. So this one is slightly less nitrogen rich than this one, but they're both well into the sufficiency range. So the story here is, what bang for the buck did you get with fall nitrogen? Sometimes, I haven't counted heads in these two plots, but sometimes you will see some better stooling, some better tillering, but in this case it looks like they're both pretty good. So sometimes we see a yield increase with fall nitrogen, sometimes we don't. In fact, more often than not, we don't. But there are certain producers, they plant a little bit later and they're worried about stress in the late fall, early winter, so they can benefit from some fall nitrogen. But other than that, I'm not real keen on fall nitrogen. And you can see that the biggest bang for the nitrogen buck came from the 90 units in the spring. That's what really made the difference here. Now we're going to go back to the 1-1. So that's 3-7 and 4-7. Notice potassium is still, by Waters and us, still deficient. Okay? Now we're going to go back to those first three plots on the very front down this corner. 1-1, 1-2, and 1-3. This area had a phosphorus soil test. It's shown on the sign, STP of 68 pounds an acre. Anybody happen to know what the fertilizer recommendation at 68 pound soil test P is?
0.
Bingo, it's 0. However, to be fair to all our friends in industry who have fertilizer to sell, Dr. Ritchie set up a low rate based on an estimated removal of about a ½ pound of P2O5 per bushel, which worked out, he's assuming 90 bushel wheat, which is not a bad thing to work with in the state.
That's what it had last year. Here.
Right. And then he put on a bust the budget, do not hold back 120 pounds P2O5. What I want you to see is what was the influence of the soil test by itself and then plus the added fertilizer on the phosphorus values by plant analysis for 1-1, 1-2, and 1-3.
You would also get to look at the balance sheet.
Sure, it's pretty obvious what that's going to be. In other words, if you're using plant analysis to test your nutritional management, okay, this one has a plant analysis of 0.34% P. I put on 45. What's that going to cost me? About 16 bucks, 18 bucks an acre? That's 0.32. So I just spent 18 bucks an acre and I didn't improve my plant tissue phosphorus at all. Now we go up here where I spend, 36, probably about 60 bucks an acre. What do I have? What's the analysis for 1-3 for P? 0.33. So in reality, this confirms that in fact, at least in terms of phosphorus nutrition, this is adequate. The soil test P did not need to be increased by adding fertilizer. By the way, I am not anti-fertilizer, but I am anti-fertilizer when it costs money that could be better spent in somebody's operation somewhere else. Okay, advance your packet to page 110. Okay. All right, this is a check plot. It turns out there is a gradient in soil test phosphorus, say 68 down there, 16 here. That's a bit of a planter bollocks up right there, so the sign there reflects the regular seeding rate, okay? Notice you've got a lot of openness here. You've got a lot smaller leaves, a lot less tillering, so that's kind of a classical phosphorus deficiency in wheat. Wheat doesn't turn purple like corn, okay? It just doesn't do that. It's stunted. This crop is effectively stunted. It's not tillered out well, and that's what's going to be a yield limiting factor. Clearly, at 16 pounds, we're going to recommend some. The recommended rate was applied there in the fall. What, October? I forget.
Yes, yeah.
October, Jesse, when that was applied in the fall? October, early November. And this one was applied January 30th?
Yeah, it was right before we put on the first shot of nitrogen. So.
Yeah, because the wheat here, because we warmed up here and the wheat hit the right growth stage, the nitrogen went on pretty close to this, so it was put on. Now, if you look at the data, this is 110. It has a very low P test of 0.2%. That's clearly insufficient. 111 over there, which looks significantly better, has a P tissue test of 0.25%. And the spring one, which is 211 right beside it, has a P tissue test of 0.29. But which one of those crops do you think is going to make the better crop? By the way, the recommendation is the 110. So even though that one has a lower tissue P, it's grown into that phosphorus. And this one here, because it got stunted in the fall, it never quite recovered. So this is a clear case where with phosphorus, waiting to correct your problem, you're shutting the door after the horse has been stolen. Okay? I know, but my wife has horses, so I have to put up with this analogies. So that's the point I want to make about that. You can't really make up for it by waiting until springtime to try to correct the problem. Now, some of the micronutrients you can wait a little longer. I don't like that idea. I like what you said before about trying to get your problems all corrected at seeding time or even before you plant your crop. Any questions?
So with the tissue test phosphorus, I guess even though it gives you the same reading,
Slightly higher, actually.
pull soil samples, right?
Yeah, but if you run the green seeker over that one,
Yeah.
this one's gonna come up better number, even though because it's got better biomass.
Yeah.
So that's another way where the green seeker, by the way, the green seeker responds to biomass whether or not it's a sulfur problem, a phosphorus problem, a nitrogen problem. Just remember that. The next generation of sensors will be a lot smarter than the current generation of sensors, but they will probably combine it with smarter plants. The British have already experimented with a program where when the sensor comes over, it stimulates fluorescence of the plant if the fluorescence is under potassium stress. So in other words, the plant senses the beam coming in, sends a fluorescent photon back saying, I need potash, and then by the time the boom comes over that has the fertilizer, it'll put some down. That work is being done. We just need to do it in more crops, and we need to do it with more nutrients. Needless to say, that seed's going to cost a lot more per bag. At least for a while. All right. My last one. So those of you who still have your packet, this is a Ballard County scenario, courtesy of Tom Miller. So what you see here is what you see from the pickup truck. Okay? And then you say, I better get closer to this and see what I got. So then they went out in the field a little further and took another picture, got closer in. Okay? And then they got closer yet. So by the time you get to this one, anybody got an idea what we might be looking at? It's yellowed at the top of the plant. Is it likely to be nitrogen? Some people are shaking their head. It's yellow. Doesn't yellow mean nitrogen?
The bottom.
Typically it's going to be on the older leaves. This is something that's affecting the upper part of the plant. And then he took a photograph of some good looking or better looking wheat, which is the next picture after that. A lot more uniformity of green color in that canopy. Okay? Then what you see after that, he took soil samples. And Farm ID good means the good spots, and then the next soil analysis is bad equals the bad spots. So that's bad, that's good. Can you see a difference? Can you see a difference?
Too much mean? Or what? No, I don't understand.
Too much phosphorus. Yeah, well, you know.
I mean,
K is high, magnesium is very high, calcium is very high. If you just look at these two soil analysis sheets, you don't see much joy here. So let's flip to the first plant analysis sheet. It actually says plant/soil analysis. And it starts with the good and then finishes up with the bad. So then you start to see some differences. Sulfur, boron, You wouldn't believe the magnesium because the magnesium salt test is through the roof. So, but the sulfur salt test was uniformly 21 pounds. But the sulfur tissue test, it's 0.09. That's just plain awful. Now the boron dropped by half, but I'm not exactly sure whether the boron was being affected somewhat by the sulfur or independently on its own. But the major limiting factor here is sulfur. That's what's causing those symptomologies at the top of the plant. Now, if you look back at the salt test results, you had 21 pounds of S and 21 pounds of S, both good and bad. What is the value of a sulfur salt test in the state of Kentucky?
Apparently not.
Absolutely zero. There is no correlated calibrated salt test for sulfur for the state of Kentucky. Never been developed. By the way, in many states that do have them, 21 would be considered great value. So clearly, whatever water is detected as 21, they call it low, but they couldn't call the difference between what was clearly a good and what was clearly a bad area. The one thing in the soil result that is somewhat indicative is, turns out it's in the organic matter. In a marginal environment, sulfur is made available out of the organic matter turnover. So what was probably happening there was in those areas where the wheat was good, there was higher level of organic matter. It's about 1.8%. It's turning over fast enough, you're getting sulfur into that crop. Whereas the other area is about 1.5% and it's just marginal enough, you didn't get good sulfur. The boron also can come out of the organic matter. So that's kind of indicative to me that the organic matter is a bit of an issue here. And then Tom Miller told me all those yellow areas are where they scalped it to build terraces in the old days. All right, so now I'm going to turn you over to Dr. Ritchie.